Hi, everybody. Hi. Thank you, Liza. Thank you to the amazing organizers of this ultra mega super amazing event. I'm between you and dinner. Attention is scarce, so let's get right to it. This is why we're here today. This is the famous Keeling curve. The Keeling curve since 1958 measures the accumulation of CO2 in the northern hemisphere atmosphere. And the downtick every year is the spring and summer, where lots of plants grow, absorb a lot of CO2, while the uptick in the data is every year the winter and the autumn, when things fall down and there's less growth, but the CO2 emissions remain unabated. Now, that peak-to-peak difference, so from one tip to the next, is about 12 gigatons of CO2, not carbon, that is accumulating in the atmosphere every year. Now, why that matters is because it's just very coincidentally exactly the global carbon footprint of the oil industry. So in this amazing event today, we saw lots and lots of solutions. The problem is it's an enormous, enormous, enormous thing that we have to work off. So having to remove the carbon that is being emitted by an industry that has been increasing in production for the last 150 years and still plans to increase for the next 10 years, at least, professed publicly, is a very big problem. Normally, at this point, what we heard this morning, there's denial, distance, sort of all the barriers where people say, hang on a minute, it's somebody else's problem, the regulators have to solve it, there's all kinds of fun stuff we need to do. And so what I wanted to do is I wanted to tell a different story, and I wanted to sort of bring a different perspective, that there is room and scope for us to do things very differently. And it has to be something that's not drinking sustainably sourced coffee. Don't get me wrong, I think that's a great idea. Or wearing all-bird shoes, wonderful shoes, but the point is it's not enough. We need to do something really big. So what can we do that actually sort of changes the way we approach this giant increase and buildup of CO2 in the atmosphere? Just reminding myself, I forgot my name earlier today. So what is big enough? As a biologist, I look at how things grow. Globally, 830 gigatons of carbon dioxide cycle through the biosphere every year. That's about 430 gigatons of carbon dioxide, again, not carbon, that cycle through the land masses, and about 400 gigatons of CO2 that cycle through the oceans. Now, what does that actually look like? So what you're going to see is what it would look like from space if you could see chlorophyll year-round in space. And what you're seeing here, these orange and red swirls on the coastal oceans that sort of happen at the edge of these land masses, is what we are trying to tap into with those natural algal blooms. Now, those edge events at the edge of those continents make up about 20% of the global carbon circulation through the biosphere. It's a very, very productive system. I used to spend a lot of time in Antarctica looking at the marginal ice zones. There's a couple places that are more productive than others. And so up there, when Africa is spinning around on the left, that's where we are today in Morocco. And what you're seeing here is how things just move in the ocean all year round in very different environments. And why this is such a big deal is because it moves a lot of CO2. However, the black stuff, the land masses, there are amazing resources there too. This is why I need my notes. Why is the ocean special? In the ocean, we have 5 times more animals than we have on the land. It's a very productive environment. So what that means is that there is a biosystem that can feed all these global food chains with all the fish that we benefit from. And there's 5 times more animal lives. There's 50 times more nitrogen available at any one point in time in the ocean than all of global nitrogen sources and man-made ammonia combined. So there's a lot of nitrogen in the ocean. There are 38,000 gigatons of CO2 available. In the atmosphere, it's about 860 gigatons of carbon, sorry. 38,000 gigatons of carbon, 860 of carbon in the atmosphere. That's about 44 times more carbon in the ocean than in the atmosphere. It's a rich environment. Now, it's an unfamiliar environment. We don't see big forests and agricultural landscapes in the ocean. We love the seaweed that we just saw. All kinds of really cool places and beautiful coral reefs and wonderful productive environments. But it's not a familiar environment where we see lots and lots of plants growing in the way that we're familiar with on land. If you look at the standing biomass, how much carbon is in the biomass, it's actually in the ocean, it's an upside-down food pyramid. What's very strange about the ocean is that there are lots of carbon in fish, but actually very little in the little tiny microscopic plants that are growing in those swirls that you saw. The point is, the reason why that works is because it's an extremely fast turnover, high throughput system. Those algae really grow fast. They move a lot of resources by just circulating very quickly. There are no roots, no leaves, no branches, no trunks. It's just all plant that's being consumed by the various animals in the ocean. So the fact is it's a very fast system, and those blooms that you see are very quick events. Now, there's another resource out there, which is empty desert land. If you think of the 18.5 million square kilometers of hot desert is the kind of desert that you think of as arid, dry, sandy places like the Sahara, the Arabian Peninsula, places like that. So that's too soon. Let's go back 1 second. 18.5 million square kilometers of hot desert is important because there's a lot of coastal desert right at the edge of the oceans. It's a place where you get a lot of renewable energy. You have cold ocean, hot desert, usually means a lot of wind. Obviously, they're very sunny places, so lots of renewable energies from solar as well. Where we are in Morocco, we're surrounded by wind farms, by many gigawatts, actually terawatts of wind and solar both. And that Moroccan renewable energy grid is growing very quickly. And that can be true in most coastal deserts around the world. So what is our proposition? Our proposition is to do this. We take the water from the ocean. We take deep water that didn't make it to the surface from below the mixed layer depth. So it didn't contribute to the euphotic zone. We put it in a little lab over here. We grow a monoculture of local algae, and we'll talk about that in a second. It's still sort of under lab conditions. We then take it into a greenhouse where it transitions into the outdoor conditions, goes to a little pond, biggest pond, and then we harvest it. We take the algae out of the water, and over the years what we've learned is how to do this really simply. It has to be simple working in difficult environments like this. So what that means is when the algae get hungry, we add more seawater. When the pond is full, we transfer it to the next bigger pond. When that pond is full, we can repeat the cycle until we get to the harvesting stage. Now, the reason why that matters so much is it's got to be operationally simple to be working in places like the Atacama Desert in Chile, in the Baja California, Sea of Cortez, Namibia, South Africa, southern Angola, the west coast of Morocco, the Mediterranean, Red Sea, Arabian Sea. There are lots of places, Australia. They have to be in relatively politically stable places, but the fact is they're usually very remote, and that's why they have to be simple. The other thing is it has to be quite low cost. So we've learned from shrimp farmers how to pump the water once, and then it percolates by gravity through all these ponds. No more pumps, very little electricity cost. We've learned from the miners how to remove fines in their language, little tiny particles from the water, our microalgae. We remove over screens that, again, are gravity-fed, again, reducing the energy demand. We've worked with the University of Southampton, running the second largest supercomputer in the UK to improve the performance of our paddle wheels. And we thought we could eke out maybe a couple of % of improvements. We're now at 87% in the reduction of energy demand for our paddle wheels by simply studying the computational fluid dynamics and then building model ponds to test the ideas. The point is it has to be super affordable. What does that mean? When we harvest here on the left, we run the water down these screens, the water goes through, the algae gets retained. We have a sort of pea soup, thick kind of slurry, which is very simple to pump into the desert for solar drying. Again, saving a lot of energy. And we end up with this very dry, very salty biomass that is really quite indigestible. It's cross-linked with all the UV light, but we also pickle it. So what we want to bury is pickled, super dry, super salty. I'm talking about 40% salt. Think of the pickles in your refrigerator. They're about 1.2% salt, right? So this is really salty stuff. And it's actually very difficult to process once it's been dried that way. We can bury that on site, so there's no scope 3 logistics emissions. We can bury that on site in a way that it stays there for thousands of years and we mummify it. Now, what we want to do is we want to take advantage of this process, and we want to do this worldwide. So this is an example, an illustration of what a 1,000-hectare production site looks like. 1,000 hectare is the first full-scale commercial farm that we want to build. It's right in the same place in Morocco where our existing experimental farm is. It takes advantage of all those lessons learned. We've now done this in South Africa. We've done it in Oman. We're doing it in Morocco. We've had 10 years of field experience. And what's really important about this is that it is something we can do worldwide in all those desert countries. There's one really key ingredient we've heard about all day, which is biodiversity. We work with local algae. 4 of our production organisms that we really like, 3 of them were isolated within 1 kilometer of our existing site, and the 4th one was isolated less than 10 kilometers away. The ocean is very niche-y. It's very local. Actually, those organisms have had hundreds of millions of years to sort of adapt and acclimate to those environments. If we work with the beautiful, wonderful model organisms in university sort of culture collections, they've been sitting for 100 years on very dark, dingy shelves, and they don't want to grow in the desert. 1/3 of all biofuel companies failed in the first 12 minutes of field trials. We, in contrast, have been working in the field from the beginning for the last 10 years to work out how to make the scale-up happen and how to do that. Now, having said that, the last question is, how do we, we can produce about 100,000 tons of CO2 offsets with a 1,000-hectare farm. So we've done a global GIS search where we look at ideal land, super close to the ocean, no obstructions, no commercial activity, no plant life. These are truly empty deserts. This site is a salt pan. You couldn't grow a blade of grass. And how do you make that happen on a global scale? And so we estimate that there's about 500,000 square kilometers of ideal land that's available for this scheme in politically relatively stable countries. And that's about the size of the sugarcane crop worldwide. Again, we're very, very productive per unit area. We can sequester 30 times as much per unit area as a temperate forest can in terms of carbon buried. And so the point is we want to now scale this up all over the planet. And the reason why that excites me is because we're already doing a lot of the homework, a lot of the work to sort of anticipate how to go to Chile, how to go to Australia, how to go to all these other locations, and putting the systems in place now. The other bit is that you're going to ask about MRV. We heard a lot about MRV. It is truly additive. We're taking deep seawater that would not have reached the surface. We're pumping it to the surface. We're adding local algae. We're creating a lot of biological activity that sucks in a lot of CO2. We trap that CO2 in the biomass. We sink it in the desert. We put the oil back in the desert. Remember, oil originally was algae that settled out in shallow oceans, right? And so we're just putting the oil back in the ground. And then once we've done that, we return the de-acidified seawater to the local ecosystems. That's very exciting. So having said that, what I challenge you to do is to think big. All of us today, all the wonderful investors and inventors, we need to think big. And on that 500,000 square kilometers, we are firmly convinced that we can sequester 2 gigatons of CO2 per year. I actually believe we can do more. That's a conservative estimate. So I want all of us to imagine a different future. I want us to imagine a future where all of your solutions get big, make a big impact, help to reduce the sort of emitted carbon in the first place, find alternative ways of doing all those wonderful things we've heard today. Hydrogen, microgrids, electric mobility solutions, educating CEOs, seaweeds, reducing, eating less meat, making fusion happen, right? The point is we need all the solutions, but we're trying to do our bit, and thank you very much. Let's all have a really delicious drop now, and see you at dinner.